All right, let's take a look at mole fraction. This is chapter 5, and this is the last part of chapter 5, which deals with gases. It says, what is the mole fraction of hydrogen in a mixture that's 12.54 grams of hydrogen, 60.67 grams of nitrogen, and 2.38 grams of ammonia? Well, hopefully you remember this formula, that mole fraction of a substance, and in this case, we're looking for the mole fraction of hydrogen, is going to be equal to the number of moles of hydrogen divided by the total number of moles. Okay, so we need to calculate the number of moles of hydrogen, and unfortunately, we're going to have to calculate the number of moles of nitrogen and ammonia too. If you're thinking all I have to do is take these masses, like 12.45 grams of hydrogen, and I divide that by the molar mass of hydrogen, which is 2.02 grams per mole, and I end up with 6. What is it? I can't read my writing. 6.16 moles of H2. You'd be absolutely right. So there's hydrogen. We do the same thing for nitrogen. So 60.67 grams of nitrogen. And the molar mass of nitrogen is 28.02 grams per mole. And we end up with 2.16 moles of nitrogen. Then I guess I'll have to do ammonia down here. We have 2.38 grams of ammonia, and the molar mass of ammonia is 17.03 grams per mole. You divide that, and you end up with, oh boy, 0.140 moles of ammonia. And now we can plug some numbers in, and we can say the mole fraction of hydrogen is equal to 6.16 moles divided by 6.16 plus 2.16 plus 0.140 moles. And the moles cancel out, and we end up with a mole fraction of hydrogen, which is equal to 0.728. And so there's our answer like that. The next slide is a really interesting experiment, which I think you'll find kind of neat. It says collecting a gas over water. Now, oftentimes when we need a gas in the laboratory, we can simply buy it in what's called a lecture bottle. And I'm not kidding, that's what it's called, is lecture, like a lecture that you're in right now. So it's basically like a small kind of scuba tank almost, right? It's really tiny. It's probably only about 30 centimeters long, and it's got a regulator that you can put on it. And let's say, I don't know what kind of gas you might want. Maybe it's, let's say, sulfur trioxide just for fun. And then you would be able to, regulate it with the knob or whatever, and you could get the gas like that. But if you need a really small quantity of gas, buying it is not always the best way to get it. Sometimes you can just generate a gas. Like, let's say, for example, you wanted a small amount of oxygen gas. Okay, is there an easier way to get oxygen gas than just buying it? Right, which you can totally do that. But the answer is yeah, absolutely you can. And it's a pretty simple experiment. Let me walk you through it because I find this slide or this picture, this figure, a little confusing. Here's what you do. Okay, you start out by taking a big graduated cylinder. And if you're thinking, we don't have graduated cylinders that look that big, like maybe even a 2 or 3 liter graduated cylinder. Yeah, it's a big graduated cylinder. And you fill it up to the brim with water. Okay, so there's water spilling over the sides. And then you take a piece of plastic or something and you plop it on top so that the graduated cylinder is completely filled with water and nothing else. Okay, so there's no gas in there at all. It's just completely water. Then you take your hand, okay, this is the human hand. You take this thing and you invert it, whoop, upside down into a big, basin or bin of water. And when you've inverted it into that water, then you rip off or you pull off the green cover, okay? So that you have the inverted graduated cylinder and it's filled with water right to the top. So there's no gas in there, there's no air in there. I know there is here, but we're gonna get to that. Give me a thumbs up if you follow me on that part, just getting that far. An inverted cylinder in a basin of water so that it's filled with water and there's no gas in there. Good, thanks, Chris. Thanks, Julius. Okay, next what you do is you do the reaction that produces the gas you're interested in making. Now here's just a particular example. It says if you take potassium chlorate and you heat that up, and you're just literally heating it with a Bunsen burner, it produces potassium chloride, which is a solid. That's not a gas. but it's also going to produce some oxygen. Where's that oxygen going to go? If you have the test tube stoppered and you have a piece of rubber hose, that oxygen is going to go, and you're going to put that hose and you're going to put it up into the water here. And then the bubbles of oxygen are going to go up and they're going to start to displace the water by pressure, and they're going to push the water out. And so what you're going to do is that headspace here, this is going to be filled with oxygen gas. Okay. Now, whoever it was really eager. They produced so much oxygen gas that they filled the whole dang thing up with oxygen gas. Okay. But give me a thumbs up if you follow me on this method of forming a gas. Kind of interesting. Kind of a neat way to make a gas. Good. Okay. So one thing that I want, and this is the whole point of this slide after you kind of walk yourself through the figure, is this. When the person was using the Bunsen burner and heating up the potassium chlorate to make the oxygen, they started collecting oxygen in here. But remember, water has a vapor pressure, right? Now, if you stand with your face over and you're looking over a cup of water, you're not going to feel the water, pushing. You're not going to feel water vapor pushing against your face, okay? Because it doesn't have a lot of pressure, but it's got some pressure. Even though you don't feel it, it's there. And so the total pressure of what's in there, yes, it's mostly oxygen gas, okay? But there's also going to be a little bit of pressure from the water vapor, okay? So that's why I made sure to put the letter G. Oh my God. Okay, there we go. Highlighter. That's why I made sure to put the letter G here, okay? So the total pressure inside there is not just from the pressure of the oxygen, it's also from the pressure of the water. Now you're probably thinking, well, come on, Mr. Dion, you just said that you're in the lab, you're doing a reaction at atmospheric pressure. Really, man, how much pressure can water have at atmospheric pressure? Is it going to affect my answer? Well, the answer is yes, okay, it will. And if you're wondering, well, how am I going to know what the water pressure is at a certain temperature? You look it up in a table, okay? So let's say you're doing a reaction at, I don't know, around 25 degrees Celsius, okay? Let's say you're around 25 degrees Celsius. You can see that they've given you the vapor pressure of water in millimeters of mercury. You can convert that to atmospheres. You can convert that to pascals or kilopascals. And so you would, in order to calculate, and I'm going to back up here, if you wanted to calculate the pressure of the oxygen here, PO2, it's going to be equal to the total pressure, subtract the pressure of the water. And that equation is going to be important when we look at this practice problem right here. Example 15.15. Oxygen gas is generated by the decomp of potassium chlorate, just like in that figure that we looked at. The volume of oxygen that's collected at 24 degrees Celsius and atmospheric pressure is 762 millimeters of mercury. So this is here. This is our P, our pressure, our atmospheric pressure. Okay. Calculate the mass in grams of the oxygen gas obtained. So this is our total pressure. Okay. The 762 millimeters of mercury. That's our atmospheric pressure. And so that's going to be the total pressure that we're going to need to displace the water. But they've given us the pressure of the H2O. They've given that to us right here. And we know that the total pressure is equal to the pressure of the oxygen gas plus the pressure of the water vapor. Therefore, we can rearrange this to say the pressure of the oxygen gas is going to be equal to 762 millimeters of mercury, subtract 22.4 millimeters of mercury. That gives us a pressure of 740 millimeters of mercury, 740 millimeters of mercury. Can we convert that into atmospheres? Well, we know that in 1 atmosphere, we have 760 millimeters of mercury. And so we end up with a pressure, and I've calculated this already, we end up with the pressure of our oxygen as being 0.974 atmospheres. Okay, that's the whole key of the question, because we're given the volume. Our volume is 0.128 liters. We're given our temperature, 24 degrees Celsius, which is 297 Kelvin, and we're asked to calculate the mass of oxygen in grams. If we know the number of moles of oxygen, we could calculate the mass of oxygen from that, couldn't we? Let's use the ideal gas law. PV is equal to nRT, and let's solve for N. N is equal to PV over RT. We plug in our pressure, 0.9, what is it, 0.974, sorry, atmospheres, multiplied by our volume, which is 0.128 liters, divided by our gas constant, 0.0826 liters atmospheres per mole Kelvin. Our temperature, 297 Kelvin. And when you punch all this in, you get the number of moles of oxygen, which is equal to 0.00511 moles. Well, we know that in 1 mole of oxygen, we have 32.00 grams of oxygen. When we punch that into our calculator, we see that moles cancel out, and we end up with the number of grams of oxygen, which is 0.164 grams of O2. Give me a thumbs up if you think you can solve that one, maybe with a little practice. But the whole idea is that we have to subtract the pressure of the water vapor in order to figure out the pressure of the gas of interest. Okay, let's go right back to the beginning of chapter 5 when we first started discussing what's called the kinetic molecular theory of gases, where we say in this theory that a gas is composed of tiny discrete particles, whether they're atoms or molecules of a gas. The particles are in rapid constant motion, going in straight lines. Particles are far apart compared to the size. Most of the volume of a gas is empty space. Ideal gases consist of particles that have a mass, but they don't have a volume. And you're thinking, well, they do have a volume. Again, this is the theory of ideal gases. So the particles, instead of having a volume, we think of them as just little dimensionless points. Now let's add on to that kinetic molecular theory of gases now and say the attractive and repulsive forces between the gases is negligible. Remember, there's no such thing as an ideal gas, and you guys know about intermolecular forces. So of course gases do experience intermolecular forces, but using the ideal gas law, we can assume that the attractive and repulsive forces can be negated. The average kinetic energy of the particles is proportional to the absolute temperature in Kelvin. So the particles of a gas do not all possess the same kinetic energy. There's going to be an overall distribution of energies. Some of them are going to have more kinetic energy than others. Two gases at the same temperature are going to have the same kinetic energy. But as the temperature approaches absolute zero, the kinetic energy of molecules starts to approach zero. And finally, the average kinetic energy of the particles does not change with time at a constant temperature. So the collisions between particles and the walls of the container are elastic. Kinetic energy is conserved, but may be redistributed. Well, that's a lot to chew on. And let's go back to the speeds of these gases, of ideal gases, and look at a couple of graphs here. You might be wondering, well, how fast do gases move? Is there a way that I can calculate the speed of an ideal gas? And the answer is yes. Before we look at how to calculate that, I want to get you to focus your attention on the left side of the slide. It says here the distribution of speeds for nitrogen gas molecules at 3 different temperatures. So all 3 of these curves represent nitrogen gas. Nitrogen at 100 Kelvin, 300 Kelvin, and 700 Kelvin. Now, on the x-axis, we have molecular speed, and on the y-axis, we have the number of molecules. What's the take-home message from these 3 curves? Is that as we increase the temperature, the average molecular speed increases, right? You can see that overall, the average molecular speed does increase as we increase the temperature. As we increase the temperature, we also get a wider range of speeds of the gas molecules. But again, it still stands that the speed must be proportional to the temperature. Let's look at the formula that we would use to calculate what's called the root mean square speed. That's what the RMS stands for. Where it says RMS, this means root mean square. And this is how we calculate the average speed of a gas molecule. We say the root mean square speed, which is the small u. We use that for speed, so little u is speed, is equal to the square root of 3 times r. And the r that we use here is not the one that you're usually used to using. It's 8.314 joules per mole Kelvin, multiplied by temperature, divided by big M, and big M is molar mass. Well, if we go back to this curve or this graph again, what does it tell you? That the speed of the molecules, or their average speed, is proportional to their temperature, right? Because temperature is in the numerator. Now I want you to look at the graph that's on the right-hand side of the screen. Here's the distribution of 3 different gases, but they're all at the same temperature. They're all at 300 Kelvin. And you notice that when you have a light gas, like helium, which only weighs 4 grams per mole approximately, its average speed is much greater than that of nitrogen, which is 28 grams per mole. And its average speed is even more than that of chlorine, which is around 71 grams per mole. So what's the take-home message? Is that as temperature is held constant, the heavier the gas, or the higher its molar mass, the slower the average speed. Well, that makes sense based on this formula, because root mean squared is inversely proportional to molar mass. As molar mass increases, root mean square speed decreases. This is called, or based on, what's called Graham's law. Now let's apply Graham's law qualitatively. It's a really easy question to answer because you don't have to do any math. Hydrogen has 2 naturally occurring isotopes, hydrogen and deuterium, which is hydrogen 2. Chlorine also has 2 naturally occurring isotopes, chlorine 35 and chlorine 37. Thus, hydrogen chloride exists as 4 different types of molecules. We have them all here. Who could tell me which one of these is going to move the slowest and which one will move the fastest? I'll give you a second to look at it. Well, if we calculate the molar masses of these gases, molar masses, for the first one, it's going to be 1 plus 35, so that's 36 grams per mole. For the second one, it's going to be 1 plus 37, which is 38 grams per mole. So the next one is 2 plus 35, which is 37 grams per mole. And for the last one is 2 plus 37, which is 39 grams per mole. The one that's going to move the slowest will be the one that weighs the most. This will be slowest because we know that root mean square speed is equal to the square root of 3 times the gas constant times T divided by molar mass. The fastest one is going to be the lightest one because, again, root mean square speed is inversely proportional to mass, so the lightest one is going to move the fastest. And so the answer is C.